So what we're going to do is prove that the busy beaver function is not computable. And as you guys will see, that will turn out to be a pretty useful result. So we're going to use the same method we always use. So what we're going to do is we're going to proceed by reductio. So we're going to assume that the busy beaver function is computable, and then use that to build an evil Turing machine, which does something impossible, and conclude that the busy beaver function was not computable after all. So we assume otherwise. In other words, we assume that some Turing machine M busy beaver computes and of course, what it means for this machine to compute the busy beaver function is that if you start this machine with a tape which is blank except for K1s, then it'll output busy beaver of K1s and stop. So what we're going to do, we're going to use the busy beaver machine to build the evil Turing machine, ME. And it is super easy to build. So I'm just going to describe the plan informally first. So the way the evil Turing machine is going to work is we're going to start it out with an empty input. And the first thing it's going to do is write down n1s for some large n. And then it's going to duplicate the size of that sequence. And then it's going to use the busy beaver machine as a subroutine to compute the busy beaver number of that string, the one it just generated. So basically, it's going to compute busy beaver of 2n. And then it's going to add 1, and it's going to stop. Super simple. That's all it does. So print n1s, duplicate string, apply busy beaver, add 1, and stop. Now, something to note here is that n here is fixed. So n is not the input we give it. So this is what it does on an empty input. So in specifying the program, we have to say in advance what number n is going to be exactly. And I have not yet given you enough information to know what it is. So the one thing I've said, and that's going to be crucial, is that n is large. So what I'm going to do is I'm going to go on, and then I'm going to come back to tell you just how big it needs to be. So let's count the states in E. So maybe I'll give letters to, or numbers to these. OK, so for 1, so how many states do we need to print n1s and then bring the reader back to the beginning of our string? There are much better ways to do it. But one way to do it is to just use n plus 1 states. That is like the kindergarten way of doing it. Because what you do is you just start with a state that says, print a 1, go right, and go to the next state. And then the next state says, print a 1, go right, go to the next state, and so forth until you get to the nth state, which just says, OK, now start going back. And then the plus 1 just tells you when to stop. So that'll do it. I mean, there are much better ways of doing it. For example, a different way to do it would be to start out by writing the thing in binary notation, and then have a fixed number of states that extends it into the unary notation way. So for small numbers, that's going to require more states, but for big numbers, that's going to require much fewer states. OK, but this is all we need for these purposes. OK. For 2, we need to duplicate the string. So that just requires some number b, which is independent of n. And that's the crucial thing. Doesn't matter how big it is, it just means that it's independent. But in fact, we know that it's quite small. In fact, I think that designing such a Turing machine is a homework exercise. Now, for 3, the number of states we need is exactly the number of states in the Busy Beaver Turing machine, MBB. And again, crucially, this number is independent of n. So it's just constant relative to n. And finally, to add 1, we just need some small number of states, c, which again is independent of n. So here is the number of states in our evil machine. It's just n plus 1 plus b plus that guy plus c. In other words, it's just n plus some constant beta. This means that it's easy to pick n big enough so that the following is true. If you just pick n to be bigger than beta, then that condition is going to hold. And this is the trickiest part of the proof. So the trickiest part of the proof is just to keep track of the fact that n is fixed. It needs to be fixed from the start. But I didn't tell you at the start just how big it was going to be. I only was able to tell you now that we have beta on board. And the reason I did that is that in order to know what beta was, I first had to explain how the machine worked. But if one was doing this, if one had unlimited amounts of time and patience, then the way to do this would be to very carefully see what B is and see what C is. You're, of course, never going to know what that is because it doesn't really exist. But our assumption is that it does exist, so you would be able to calculate it. And that would be enough to know what beta is. And that would be enough to know what n is. And then you just build that into the specification of your machine.